All right, on to section 2. We're going to look at changes of state. Now, the three most common states of matter are solids, liquids, and gases. And I'm sure you've observed that a piece of ice that started as a solid, when the temperature is increased, it will turn to a liquid, and when it is increased even more, it will turn to a gas. We're going to look a little bit more specifically at what's happening to the particles when this happens. Now, here is a diagram. We're starting with 1 gram of ice, and we're starting at a temperature of 243 Kelvin. Now, from 243, adding heat, we're adding up to 61 joules of heat. I still have ice, but what's happening is that the kinetic energy, when you add heat, the kinetic energy of those particles increase. And when kinetic energy increases, temperature increases. So from here to here, my particles are moving faster and faster and faster. They're still in the solid state until it reaches 273 Kelvin. Then they get to the point where the particles break free of one another. This is called the melting point. Point B is the melting point. So I'm going from ice and I'm adding 61.7 joules of energy, of heat, to break those particles free of one another. So they had to overcome some very powerful forces. Now, notice that from adding 61.7 joules of heat all the way up to 395, so I'm still adding heat. But what's happening to my temperature? It's staying the same. How can you add heat but temperature stays the same? Good question. All of this heat that is being added is being used to overcome the forces that are holding all of the particles together in the solid state. So as soon as it hits that 273, that's the melting point. That's not when all of a sudden you had an ice cube and now it's all water. No, they're overcoming that force, and there could be, this is ice and water. So from here to here, you might have chunks of ice, but as soon as you hit this 395.7 and you add more heat, your ice is going to be completely gone. So when you add more heat than this, you now have an increase in temperature, because when you add heat, the kinetic energy increases. So this is here's my solid state, melting point. Now I have my liquid state. This is water. So again, as kinetic energy increases, temperature increases, and I've gone from about 400 joules of heat to about 800 joules of heat, all staying in the liquid form as the temperature increases. Then I get to point D, which is my boiling point. Now once I get to this point, which is at 373 K, or 100 degrees Celsius, my particles, notice that I'm at another flat line. So water is boiling and the temperature is staying the same, because to going from 813 to 3073 joules of heat, that's a lot of heat, which means that those water molecules that are in the liquid state are fighting really hard to leave that state, and they need to have so much energy to leave that liquid state and to become steam. It requires a lot of energy. So going from boiling point to steam is a very large transition. So that means when you're making your macaroni and cheese, that you don't have to have your burner turned up on high to boil. If it's boiling at the 6, it's still the same temperature. It's not going to make it go any faster, even though we really hope that it does. Now, as in melting, the temperature does not rise when the liquid boils. We know that. These two phases, though, this phase is called our heat of fusion. It takes energy to, as you can see, it takes energy to melt ice, even though the temperature is not changing. It takes energy to boil water, even though the temperature is not changing. So this part of our graph is also called our heat of fusion, and this is our heat of vaporization. How much energy does it take to vaporize a liquid? So, when calculating the heat that's required to melt a solid, we would write it as H of F. Heat required to melt a solid is mass times my heat of fusion. To calculate the heat needed to vaporize a liquid, I would write as Q equals M times heat of vaporization. So, if I gave you an example, like the example problem on page 325, says, suppose that you are camping in the mountains and you need to melt 1.5 kilograms of snow at 0 degrees Celsius and heat it to 70 degrees Celsius to make hot cocoa. How much heat will be needed? So if I'm starting at 0 degrees Celsius, which is the same at 273, I'm starting right here. This is my starting point. I need to get to 70. So, I don't know, somewhere around here. I need to get from here to there. I can't just start and say that Q equals M times C times delta T. I can't just do that because it takes energy to overcome that solid state. So in order to do that, this is a couple part question, I need to find out what heat is required to melt that snow or that ice. And then I need to figure out how much heat is required to go from here to here. So I need to figure out this step and then this step. So I would say Q is equal to, the mass was 1.5 kilograms, times, what's the heat of fusion of water? You would find that on page 324 on table 12.2. The heat of fusion is 3.34 times 10 to the 5th. And this is joules per kilograms. So my kilograms will cancel, and again, Q is heat. I would get, if you do the calculations, 5.01 times 10 to the 5th joules. Now that's great. That's how much heat is required to melt the snow. Now I need to go from 0 up to 70 degrees. This is when we're going to use the equation that we used previously, which is the Q equals M times C times delta T. So, what's my mass of the water? I still have 1.5 kilograms. What's my specific heat of water? You're going to need to flip back to page 318 to find the specific heat of water, which is 4180. And then what's my change in temperature? Going from 0 degrees to 70 degrees, I would have a 70 degree change of temperature. And one change in Celsius, one change in 1 degree Celsius is equal to 1 Kelvin. So a 70 degree difference in Celsius would be the same as 70 Kelvin. Doing this math, I should get my Q would equal, I know this is kind of crammed in here, 4.39 times 10 to the 5th joules. So that's how much heat is required to get from here to here. So how do I find the total amount of heat needed? I would need to add my 5.01 times 10 to the 5th plus my 4.39 times 10 to the 5th, and you should get 9.40 times 10 to the 5th joules. That would be my total heat needed. That's to go from a solid to a liquid to a gas. Now what happens if I'm going backwards? What if I take steam and I were to condense in go this direction. There, I would use the same formulas, but I would, since heat is being removed and not added, this would become negative. All that's signifying is that energy is being removed from it, and that energy is being transferred from the sample to the external world. That's what that negative would imply. So if a problem were to say you're starting with a certain mass of something and let's freeze it, you would go through the same step processes. You would just you would have a negative in front of your. Same thing. If I'm starting with a liquid and I want to freeze it, you would still do your from here to there, and from there to there, you would just have negative amount of heat. You would be extracting heat.